There was some problem in the recording of the first lecture of chapter 5. So let me reiterate or revise that for you. Um, I think the recording went bad after we calculated the eigenvalues. So the eigenvalues were 2 and -1. And then I told you there were two checks. One of the checks is that the trace of a matrix is the sum of the elements on the main diagonal, which is sum of the elements on the main diagonal, and this is equal to the sum of the eigenvalues. And the second check is that the determinant of a matrix is the product of the eigenvalues. So whenever you compute eigenvalues, you should always check whether the sum is the trace or the product is the determinant. So for this matrix, the trace is 4 plus minus 3, which is 4 plus minus 3, which is 1, and the sum of the eigenvalues is 2 and -1, which is 1. The determinant of this matrix is -12 plus 10, which is -2, and the product of these two eigenvalues is also -2. And then we computed the eigenvalues of then we computed the eigenvector for the eigenvalue corresponding to 2. So we form this matrix A minus lambda 1 I, which is 4 minus 2. So eigenvalues on the main diagonal are subtracted, and we want to solve this equation A minus lambda 1 I x1 is equal to 0, where we want to find x1, and obviously this is, if this is some matrix B, then this is B times x is equal to 0, which means that B x1 lies in the null space of this one, or x1 lies in the null space of A minus lambda I. So if we do that, so if we subtract the eigenvalue of 2 from the main diagonals, from the elements on the main diagonal, we have 2 minus 5, 2 minus 5, and then we do the reduced row echelon form for this one. So if I do minus row 1 plus row 2, I'll get 0, 0. And then if I subtract, then I divide the row 2 by 2, I'll get 1 and minus 5 by 2. So this is a pivot variable, and this one is a free variable. So this one is a free variable. This one is a free variable, and then the answer is in terms of the free variable. So this is 5 by 2 times the free variable, and the free variable is equal to free variable. So I can, for convenience, I can take B any value, and I choose B is equal to 2, so that I don't have to deal with fractions. So this is one of the eigenvectors, and you need to note here that if x is an eigenvector, then alpha times x is also an eigenvector. Why? Because A times alpha x is equal to lambda times alpha x, and A times alpha x, if alpha x is y, then this is A times y some lambda times y. So if x is an eigenvector, then this is a line. This is the eigenspace is actually a line. So all vectors x and multiples of x are also eigenvectors. So, and if we compute the eigenvector corresponding to lambda 2 is equal to -1, again we have 4 instead of -2. I have +1 here, and if -2, I have -3 minus +1, which is -3 plus 1, and I have this matrix over here. Again, I need to find x2, which lies in the null space of A minus lambda 2I, and I can find this again by doing the reduced row echelon form of this one. And if I do that, this is the vector I have. I think this is where the recording again started to work. So I just wanted to revise this portion with you, so that if you review the video of the lecture of the first lecture of chapter 5, you will find that the recording is distorted from 36 minutes on to for the next 5 minutes, and that is why I wanted to revise this one. And this is the portion that was affected. So if you have any questions again, then you can let me know, and we can do that, do this on during our discussions on Mondays or Wednesday. So let's go back to lecture 2, or let's start lecture 2. And before we start lecture 2, let me remind you 3 things that we have done. We said there are 2 checks. The 2 checks are the trace of a matrix. The trace of a matrix is the sum of the eigenvalues. N is the order of the matrix. It's a square matrix. This is equal to the sum of the elements on the main diagonal. I is equal to 1 to n. This is elements on main diagonals. Elements on the main diagonal. And then another check was that the determinant of a matrix, determinant of a matrix is the product of the eigenvalues, and if and it's the product of the eigenvalues. So we said, so these are the two checks. So if one of eigenvalues is equal to 0, this implies matrix is singular. And a matrix is singular simply means that the determinant of the matrix is 0. Okay. And then when we were doing these checks, I also told you about matrices which are positive definite, positive semi-definite. This is chapter 6, by the way. Positive semi-definite, negative definite, and negative semi-definite. So a positive definite matrix is one in which all eigenvalues are greater than 0. Positive semi-definite is one in which eigenvalues are greater or equal to 0. In this case, in a positive semi-definite case, the matrix would be singular. In this case, matrix would be non-singular. Similarly, in this one, all eigenvalues are less than 0. In this one, eigenvalues are less than equal to 0. So whenever you have semi, this means 0 is included and the matrix is singular. Then besides this check, if one of the eigenvalues is 0, matrix is singular. We also saw if a matrix is symmetric, which was the case for the projection matrix. If a matrix is symmetric, then eigenvectors corresponding to distinct eigenvalues are orthogonal. Okay, and besides these two checks, the determinant and the trace, and if the eigenvalues is 0, one of the eigenvalues is 0, the matrix is singular, which simply means that the determinant is 0. And for the projection matrix, we saw if the matrix is symmetric, then eigenvectors corresponding to distinct eigenvalues are orthogonal. And we'll see later on, if a matrix is symmetric, that even if the eigenvalues are not distinct, we will still have a full set of eigenvectors. So a full set of eigenvectors simply means for each eigenvalue there is an associated eigenvector. So there was we actually defined algebraic multiplicity. So the algebraic multiplicity is the number of eigenvalues corresponding to a single value. And the last matrix that we saw, in which we had two eigenvalues of algebraic 0 over 1 and 2 were as 0. So we'll talk more about algebraic multiplicity later on. But the thing that you need to take away from the first lecture is these two checks and these two facts that we saw when we were deriving the eigenvectors. Okay, so let me get back to the eigenvalue problem. So the problem is this one: Ax equals lambda x. This is an eigenvector. This is an eigenvector. This is a complex or real scalar. So it's complex or real scalar, and this is called the eigenvalue. So an eigenvector is one which, when transformed by this matrix A, this is a square matrix. And a square matrix will always take it to be n by n. So a square matrix, so actually we'll have I here, and I goes from 1 to n. So there are n eigenvalues, and whether we have n eigenvectors or not, that's a different problem, and where x is not equal to 0. So this is the eigenvalue problem. So we have n eigenvalues, and n eigenvectors, maybe n eigenvectors. If we have n eigenvectors, then we'll be able to diagonalize, which is the goal of the chapter. We'll be able to diagonalize this matrix. If we do not have n eigenvectors, then we have actually the Jordan form, which is actually the last section in this chapter, and which is actually tells you all matrices, whether they have or they do not have a full set of eigenvectors, we can always diagonalize them, and the special form that we get is actually the Jordan form. From this equation, we said a minus lambda I into xi equals 0, and we said xi belongs to the null space of a minus lambda I. So the null space, so this means this matrix has to be singular, because presence of free variables, if you recall chapter 2, presence of free variables implies a dimension of null space of a minus lambda I to be greater than 0, which means implies contains x not equal to 0. Right? So this is the goal, and this is what we did in the first lecture, and we want to expand on this equation. So let's expand on this equation. So if we expand on this equation, this means this is a times x1, this is a times x2. So these are columns, a times xn equals, obviously corresponding columns are equal. So this is lambda 1 x1, lambda 2 x2, and goes on so on and so forth, lambda n x n. Okay. So this column is equal to this column. These are equal. This column is equal to this column, and this column is equal to this column. Right? Okay. If this is the case, then obviously we know from chapter 1. We can write this matrix. As A times x1, x2, xn, and this is the matrix that we defined to be S. And we defined this matrix to be S, and we said this S has columns of S are eigenvectors. Columns of S are eigenvectors. Okay, and this side can be written as a diagonal matrix times S, and this we can write as xn, again from chapter 1, xn xn, and then I have this diagonal lambda 1, lambda 2, lambda n. This is a diagonal matrix. This is 0, this is 0. This I define as to be capital lambda. This is still S. So if I look at this first column, the first column, when it multiplies this whole matrix, this lambda 1 actually weighs this first column x1, so I have lambda 1 x1. There is all the other are 0. Since all the other elements in the first column are 0, there is no combination, no effect on this multiplication, or no effect of the other columns on the summation when I multiply this matrix by this first column. Similar is the case when I multiply the second column. In the second column, the first element is a 0, so there is no contribution of x1. The only contribution is from x, and so this is x2. Only contribution is from x2, so it's lambda 2 x2, which is this column here, and so on and so forth. So this multiplication is all right, it's not a problem. So columns of S are eigenvectors, and you know from chapter 3 and actually chapter 2, if the columns are independent, I can always take the inverse of this matrix. So S inverse exists. S inverse exists because its columns are eigenvectors. So eigenvectors. How do we calculate S inverse is a different story. If I can orthogonalize these vectors or orthonormalize these vectors, eigenvectors, then S inverse is simply the transpose, because this is a square matrix. If this is a square matrix and this becomes an orthogonal matrix, and for an orthogonal matrix from chapter 3, we know that the transpose is equal to the inverse, which we'll do in in one of the later lectures. So S inverse exists because its columns are eigenvectors which are assumed to be independent, which are assumed to be independent and which are assumed to be independent. So if this is true, then this whole equation, I can write this as A times S equals S times lambda, or if I multiply S inverse on this side, I multiply S inverse on this side. So this implies A equals S lambda S inverse, or if I multiply S inverse on this side and multiply S inverse on this side, so I have or lambda is equal to S inverse A S. Maybe I write this one here. So either I can write this equation AS equals S lambda, AS equals S lambda as A is equal to S lambda S inverse, or I can multiply S inverse on this side, or I can say lambda is equal to S inverse AS. So we'll see. We'll see this matrix A is actually, we'll see in a little while, this is similar. So we say A is similar to lambda, or lambda is similar to it. This is a symmetric relationship. Doesn't make a difference whether we say A is similar to lambda or lambda is similar to it. This is known as a similarity transformation. So in a similarity transformation, the eigenvalues are preserved, and we'll see in a little while how does that play out. Okay. So just to remind you, this diagonal matrix, so A can be diagonalized only if S is a matrix of eigenvectors, Otherwise you cannot, because this is from this eigenvalue equation. So eigenvalue equation is only satisfied by the eigenvectors. So any vector that satisfies this is called this equation is called an eigenvector, and obviously only those vectors can actually diagonalize this matrix A. So let me write some more facts for you, which you need to remember. And these facts, this one is, if whatever is written here is assumed to be independent, that its columns are independent, this is always true. When you have the eigenvectors correspond to distinct eigenvalues. But it's also true for symmetric matrices, even if the eigenvalue is repeated, because we have a full set of eigenvectors. So if eigenvalues are distinct, and maybe we'll prove some of these in this or in the next lecture. If eigenvalues are distinct, then the eigenvectors are independent. This is the symbol for independence. This is not the product sign. This is the inverted pi, which is used for the product sign. Are independent. This implies any matrix with distinct eigenvalues with distinct eigenvalues can be diagonalized. eigenvalues can be diagonalized. Okay, so whenever we have distinct eigenvalues, matrix is diagonalization of a matrix is possible. The only exception is actually it's not the symmetric. You actually, there's a family of matrices which we'll call normal matrices. So all normal matrices which include the symmetric, the non-symmetric, the skew symmetric, the orthogonal, the Hermitian symmetric, the Hermitian skew symmetric, and the unitary matrices, or any matrix that satisfies the normality condition, which is the normal matrix, which includes the triangular too, which is actually a very simple case. All normal matrices. So all normal matrices. So let me write here all normal matrices. And what are all normal matrices? All normal matrices implies n. All normal matrices n implies n times n conjugate transpose is equal to n conjugate transpose times n. So if these matrices commute, so if they commute, then you say, okay, these will have, so all normal matrices have a full set of eigenvectors. Whenever you have a full set of eigenvectors, this implies diagonalizable matrix is diagonalizable. Matrix is diagonalizable. Matrix diagonalizable. So all normal matrices, and normal matrix includes the symmetric, the skew symmetric, and the orthogonal matrix and their real and complex counterparts. Obviously, the triangular and the diagonal matrices also commute with each other. So this is conjugate. So this implies conjugate, which simply means you reverse the sign of the imaginary part, and T is transpose. Together they are actually called the Hermitian operator. So we can, instead of conjugate transpose, I can actually write the Hermitian operator. Here. So you need to wait until probably the last or the second last video and on this chapter, and we'll see what are normal matrices. Okay, so, and as I said before, the eigenvectors are not unique. So if X is an eigenvector, if X is an eigenvector, then alpha X is also an eigenvector. So obviously this S matrix is not unique. So diagonalizing matrix S is not unique. So this implies S is not unique. Because an eigenvector multiplied by a constant is still an eigenvector, because an eigenvector multiplied by a constant is still an eigenvector. Okay. And obviously, if S is not a matrix of eigenvectors, then S will not diagonalize A, because everything is derived from the eigenvalue equation. So if this is not a matrix of eigenvectors, if S is not a matrix of eigenvectors, then S will not diagonalize A. Obviously, the thing I've been talking about, what if you do not have a full set of eigenvectors, and we cannot have the capital lambda, we cannot have this lambda or this matrix possible. If we cannot have this matrix possible, then obviously we have the Jordan form, and that happens when you do not have a full set of eigenvectors, and that's why some of the matrices are called ill conditioned, or they do not possess independent vectors. So not all matrices. The exception is the normal matrices. So not all matrices possess n independent eigenvectors. Therefore, not all matrices are diagonalizable. However, their Jordan form is possible. Their Jordan form is possible. So Jordan form in the worst case is like this. You have lambdas on the, so these are the repeated values. So it's the repeated eigenvalues that are a problem. The distinct eigenvalues are not a problem. So you have lambdas here, and then on top of the main diagonal, you have ones, and other are zero. So this is the Jordan form. This is the Jordan form corresponding to some lambda. So remember here also, distinct eigenvalues are not a problem. Distinct eigenvalues are not a problem. The problem arises when we have repeated eigenvalues. When we have repeated eigenvalues, which is the case over here. And let me give you an example. The example is this matrix A, 0, 1, 0, 0. The eigenvalues are on the main diagonal. It's a upper triangular matrix. So lambda 1 is equal to lambda 2 is equal to 0. This is already A minus lambda I form. So this implies A minus lambda I is equal to the same matrix 0, 1, 0, 0. Didn't have to write it, but in any case, this is a pivot. So this is a pivot. So pivot in the second variable. So this implies x1 is some c constant. Sorry, it's the first variable. I'm sorry. This is the first variable. Sorry, it's the second variable. So c is 1 here and 0 here. So this is the free variable. This is the free variable. This is the free variable, and this is the pivot corresponds to c is equal to 0, and this c is equal to c. Okay. And here the algebraic multiplicity, multiplicity of eigenvalue equal to 0, of lambda is equal to 0, is 2, because there are two eigenvalues. There are two eigenvalues, 1 and 2, but there is only one eigenvector, and the geometric multiplicity of eigenvalue equal to 0 is 1, and this is equal to the number of independent eigenvectors. So there is only one independent eigenvector associated with this two. So this is the geometric multiplicity. In general, the geometric multiplicity is less than equal to the algebraic multiplicity. Is less than equal to the algebraic multiplicity. So it's a geometric multiplicity that defines whether we have a diagonal form possible or not. So these are the number of, so geometric multiplicity of this one is the number of independent eigenvectors, and this geometric multiplicity here is 1. Why? Because there is only one. So only one eigenvector. So only one eigenvector. There is none other. Instead of this c, I can take the c inside. So this is a line of eigenvectors. That is possible. So diagonalizability, so this implies diagonalizability of matrix depends on enough eigenvectors on enough eigenvectors eigenvectors whereas invertibility, which means the inverse of a matrix exists, invertibility depends on non-zero eigenvalues, So these are two different things. Diagonalizability depends on enough eigenvectors, and invertibility depends on non-zero eigenvalues. So both are not related. So you can have a matrix which does not have a full set of eigenvectors, but if it doesn't have an eigenvalue of 0, obviously this is still non-singular. So there is no connection. I cannot reiterate enough. There is no connection between diagonalizability and invertibility. Both are independent. Okay, so if an eigenvalue is repeated p times, if an eigenvalue is repeated p times, then independent eigenvectors will exist if rank of a minus lambda I equals n minus p. Why? Because then dimension of null space of a minus lambda I is equal to the number of columns minus the rank, which is n minus p equals p. This, by the way, the dimension of the null space, by the way, is also called the nullity. So the nullity is if the nullity is p, so an eigenvalue that is repeated p times, this simply means lambda 1 equals lambda 2 equals lambda p. So if an eigenvalue is repeated p times, simply means I have p of these eigenvalues, which is equal to some lambda. So if the eigenvalue is repeated p times, then the independent eigenvectors will exist if the dimension of the null space is p. So if the dimension of the null space is p, this implies p independent eigenvectors in null space of a minus lambda I. So if this dimension is less than p, obviously we will not have the independent eigenvectors. So let's do a quick proof. And the quick proof is, so this is the basis. The basis of the null space should have p independent eigenvectors to generate the eigenspace based on these p vectors. If you want the matrix to be diagonalizable, if you cannot find enough p eigenvectors, then the diagonalization is not possible, and we have the Jordan form instead of the diagonal matrix. So how do you prove if x1 to xk are eigenvectors? If x1 to xk are eigenvectors corresponding to distinct eigenvalues, corresponding to distinct eigenvalues lambda 1 to lambda k, then x1 to xk are orthogonal, are independent. I'm sorry, x1. So if so x1 are eigenvectors corresponding to distinct eigenvalues, then x1 to xk, or I say x1 to xk. So maybe I write it like this: x1 is independent of x2 is independent of xk. How do you prove that? So to prove this, we say, so the proof is very simple. We say let k equals to 2. If k is equal to 2, suppose some combination of x1 and x2 gives 0. This implies c1x1 plus c2x2 equals 0. This implies c2x2 equals minus c1x1, right? Okay. Or if I multiply a here, I have c1 a times x1 plus c2 a times x2 is equal to a times 0, which is equal to 0, or a times x1 is lambda 1 x1, so this is c1 lambda 1 x1, this is lambda 2 x2 plus c2 lambda 2 x2 equals 0. Also c2 lambda 2 x2 minus c2 lambda 2 x2 is 0, obviously. So if this is both are same, if I subtract both, I get it. If I substitute this in here, I get, or c2x2 is minus c1x1. So I get minus c1 lambda 2 x1 minus c2 lambda 2 x2 equals 0. And from here, I have c1 lambda 1 x1 plus c2 lambda 2 x2 equals 0. So this cancels, and I am left with c1 into lambda 1 minus lambda 2 x1 equals 0, because lambda 1 is not equal to lambda 2 and x1 is not equal to 0, because this is an eigenvector. This implies c1 equals 0. Similarly, I can prove for c2. Similarly, we can show c2 is equal to 0. This implies c1 x1 plus c2 x2 equals 0 for c1 equals c2 is equal to 0, which is the trivial solution, and we know from chapter 2. So this implies x1 is independent of x2. So if you have independent eigenvalue, if you have distinct eigenvalues, so this implies distinct eigenvalues, which we assumed before, but now we have shown distinct eigenvalues imply independent eigenvectors. The problem is not with distinct eigenvalues. The problem is with the repeated eigenvalues. What happens if you have repeated eigenvalues? Okay, so let's do some examples and show this is indeed true. So the example that we did on projection, so let me recall. So A equals, so this is a projection matrix. So A equals half, 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 half. This implied we had lambda, we had two eigenvalues, one was lambda 1 and one was 0. And this is what I said before. Okay, you put lambda, assume lambda 1 to be the max, the larger of the two, or the largest of the lot. So you'll always have a diagonal matrix. You'll have a matrix in which the diagonal elements are progressively becoming smaller and smaller. And what were what was S? So S was a matrix of eigenvectors, and if you recall, matrix of eigenvectors, and if you recall, this matrix was 1 1 and 1 minus 1, and we showed this is a symmetric matrix. This is a symmetric matrix, but in any case, even if this is not a symmetric matrix, for distinct eigenvalues, these two vectors are orthogonal. These two vectors are orthogonal, uh, or A times S. You can go home and check. A times S equals, what is A times S? So A times S simply means, okay, I take sum both the columns, both first two columns, which is half plus half 1, half plus half 1. So it's 1 and 1. And this means I subtract the second column from the first column. So if I subtract the second column from the first column, I get 0, 0. And this is the same as S times lambda. What is S times lambda? So S times lambda is, I pick the first column as is of S, which is 1, 1. And for the second column, this is simply, there is no contribution, so it's 0, 0. So which I get the same result here. Or lambda is equal to S inverse A S. You can also check that. Okay, so the second example is on rotation. So K is some matrix which we have done in chapter 2. It's rotation by 90 degrees. This was sine theta, this was cosine theta, this was minus sine theta, this was sine theta, this was cosine theta, and we were rotating. So this is a rotation counterclockwise, which is positive for electrical engineering sense, counterclockwise by 90 degrees. So we need to find, so the eigenvalues, we know the trace eigenvalues have to be 0. Not necessarily eigenvalues have to be real. If eigenvalues are complex, they will always occur in conjugate pairs. Why? Because your characteristic polynomial, which is k minus lambda I, if I take this determinant, this is equal to minus lambda minus 1, 1 minus lambda, and this is equal to lambda square minus, maybe I say minus lambda square plus 1 equals 0, or this implies lambda square minus 1 is equal to 0, or lambda square equals I1, lambda square equals lambda square plus 1 is equal to 0, or lambda square is equal to minus 1, which is simply I square. I is the square root of unity, a negative unity, or this implies lambda 1 is equal to plus I, and lambda 2 equals minus I. So if I sum these up, plus I minus I, get 0. So you just check the sum of lambda I equals 0, which is all right, which is the trace of K. And the next thing that you need to check is what is the product. So product of lambda I equals, so product of lambda I is equal minus I square is plus 1, which is plus 1, and this is plus 1, and this is the determinant of K. So 0 minus plus 1, this is the determinant of K. So these two eigenvalues are all right. So let's see if, so what are the corresponding eigenvectors? So if lambda 1 is equal to plus I, this implies K minus lambda 1I equals, minus I minus 1, 1 and minus I. Okay. There are many ways of solving this one. The easiest, so what we can do is we can do the previous approach. So if I do that, so let me do this right now, and maybe once more when we are doing the Fibonacci sequence. Otherwise, I'm always going to be doing the row reduced echelon form. This is just to show you there are different ways of computing the eigenvectors. There is no one particular way. Whichever is convenient for you, whichever you are comfortable with, you should try to do that. So if I do plus I row 1 plus row 2, and I'll show you both will give you the same result. If I do that, I times rho 1 plus rho 2, so this is minus I, this is minus 1. So when I do plus, so plus I square, so minus I square. Well, I think I should do minus here. I should do minus. So minus I rho 1, so minus into minus is plus, I square is minus 1. So minus 1 plus 1 is 0. And then I have plus I minus I, this is 0. Then what I do is I say, maybe I do it here, rho 1 divided by minus iota. If I do that, I have 1 here, 1 here. This is plus 1 over iota, which is minus iota 0, 0. So this is my pivot. This is my pivot, and this is the method of chapter 2. So this is my pivot. So this implies my x1 vector is going to be equal to, this is the free variable is here, so this is plus iota, and obviously any multiple of this one. So this is any multiple of this one. Now another approach is, because since we want to solve k minus lambda 1 I times x1 equals 0. Why don't I do this? I say minus I minus 1 minus I times, maybe from alpha beta equals 0. Or this implies minus alpha I minus beta equals 0. Or this means alpha minus beta iota equals 0. So from here or here, whichever I want to see, I can say pick beta is equal to minus alpha I. If this is the case, so this implies x1 equals. So if I choose alpha to be 1, if I choose alpha to be 1, so because this is only one equation and two unknowns. So if alpha equals 1, so this means this is 1 and this is minus iota. What if I pick C if C equals minus iota? If C is equal to minus iota, this is minus iota square, which is, this is minus iota square, which is plus 1, and this is minus iota, and we get exactly the same result. If it's up to you, whichever method you want to use. Okay, so and what about lambda 2 and k minus lambda 2I into x and k minus x2 is equal to 0. This implies lambda 2, where lambda 2 is minus iota. So this will become plus iota minus 1 plus iota. Again, I do alpha beta equals 0, or this implies alpha iota minus beta equals 0, or this means alpha plus beta iota equals 0. So again, I can write from here beta is equal to alpha I. So this implies beta is equal to alpha I. Again, this implies x2 equals, so beta is equal to alpha is equal to 1. So if alpha is equal to 1, beta is equal to plus iota. And what if I do the reduced row echelon form? So if I do the reduced, so from reduced row echelon form, I will get plus iota. I'll get plus iota minus 1 plus iota. Then I do iota R1 plus R2. If I do that, this will be minus 1. So this will become iota minus 1. So minus 1 plus 1, 0. And then again minus iota plus iota, 0. And then I say R1 divided by iota. If I do that, this is 1. This is minus 1 over iota, which is equal to plus iota, 0, 0. And this implies x2 is submultiple. Again, this is the pivot minus iota. So minus iota over 1. If C is equal to, minus iota, if c is equal to plus iota. If c is equal to iota, this will be minus iota square, which is plus 1, and this will be iota. So again, we have the same result. So nothing changes. So this implies the set of vectors, eigenvectors, is either this one and this one, or the other one. So we can write 1 minus iota, 1 minus iota, 1 plus iota, and these are the corresponding eigenvalues. So this eigenvalues corresponds to this one. So this is x1, this is lambda 1, and this eigenvalue corresponds to this one. This is x2, and this is lambda 2. This is I'm sorry, this is not here. This is this one. This is lambda 1 equals iota. This is lambda 2. So corresponding eigenvectors and corresponding eigenvalues. If you swap these two, then you have to swap these two too. Okay. And you can again go home and check S inverse K times S is the this one. So check. So go home and check whether this is. So, and this is what I said before. If you look at this characteristic polynomial, this is our characteristic polynomial. So we have a characteristic polynomial says coefficients are real. Coefficients are real. This implies if roots are complex, they occur in conjugate pairs. They occur in conjugate pairs. So maybe you already know this, but in any case, so if the coefficients are real, this implies roots. If roots are complex, they occur in conjugate pairs, and this is the conjugate pair. This is plus iota, this is minus iota. Again, this one is this is the rotation matrix. So if there are too few real eigenvalues, so if there are too few real eigenvalues, then there are always n complex eigenvalues. So that is what I said in the beginning of the first and the second and this lecture too. Your eigenvalues, the matrix, the eigenvalue matrix can be scalar or can be complex. The eigenvalue can be which is a scalar, can be real or complex. Okay. So what is the advantage of diagonalizing a matrix? So one of the simplest examples is, what if somebody asks you to take powers of a matrix? So what about powers and products? So powers and products. So eigenvalues, so my claim is eigenvalues of a square are lambda square I and have same eigenvectors as that of A. How do you prove that? So AX equals lambda x. If I multiply A over here, I multiply A over here, so I get A square x. The matrix always commutes with itself, doesn't make a difference whether I multiply here or here. This is already a scalar, so this is the same thing as I'm multiplying over here. So this is lambda times A times x. But A times x is what? This is simply lambda x. So this lambda times x, which is lambda square x. This is lambda square x. But what is lambda square x? So this is an eigenvector, this is an eigenvector. So obviously the eigenvalues of a square are lambda square. So we can always generalize this to an. So an will have eigenvalues lambda n, and corresponding eigenvectors would be x, right? So, and let's generalize this thing. So S and lambda, if it's diagonalizable, lambda is, so if A is diagonalizable, lambda is equal to S inverse AS, which implies, what is lambda square? So lambda square is S inverse AS into S inverse AS, but this S into S is I. So I have, I'm sorry, this is S, yeah, is I. So this is equal to S inverse A. This A and A is A square S. So lambda now has eigenvalues of lambda square, which are on the main diagonal. So now this lambda is actually lambda 1 square, lambda 2 square, all the way up to lambda n square. Okay. So in general, maybe not and, also. So in general, eigenvalues of AK are lambda I k, and each eigenvector and each eigenvector of A is still an eigenvector of AK. This is what we said over here. Okay. And, or maybe not and, or lambda k is S inverse AS 1 times, S inverse AS 2 times, S inverse AS, this is k times, and obviously this one with this one is going to be I, and so on and so forth. So this one and this one is going to be I. So this implies S inverse A raised to power k into S. Okay. Also, if A is invertible, this implies A inverse exists, or A is not equal to 0, then eigenvalues of A inverse are lambda I inverse. How do you prove this? Again, go back to the first equation, AX equals lambda x. Since A inverse exists, so we say multiply A inverse here, multiply A inverse here. So we have A inverse A into X equals lambda into A inverse X. Doesn't make a difference whether I put A here, A inverse here, or A inverse here, because this is a scalar. So this is I. So this implies X equals lambda A inverse X. What if I take X on this, lambda on this side? If I take lambda on this side, I can, so divide both sides by lambda. So divide both sides by lambda, and I can do that by lambda. Why? Because since A is non-singular, this means lambda is not equal to 0. So one of the eigenvalues is not 0. So if we do that, so this implies 1 over lambda into X equals A inverse X equals A inverse X equals A inverse X, or A inverse X in the form that we are familiar with. In a familiar form is A inverse X is lambda inverse X. So these are the eigenvalues. The eigenvalues of A inverse are lambda inverse X. So let's look at the rotation matrix. So rotates K rotates through 90 degrees. K rotates through 90 degrees. Then what does another K do? So K square rotates through 180 degrees, 180 degrees, which implies minus I, and let's see, and K inverse rotates through rotates it back through 90, so it rotates through minus 90 degrees. So let's see. So K equals 0, minus 1, 1, 0, right? And what is K square? So K square is 0, minus 1, 1, 0 times 0, minus 1, 1, 0. Or if you recall from chapter 2, when we were doing the linear transformations, this is simply, I can put cosine of 180, sine of 180, minus sine of 180, cosine of 180, and sine of 180 and cosine of 180. But let's do this multiplication and get what. So this means I am inverting the second row here, which is minus 1 and 0. And this means I'm picking the first row here, which is 0 and minus 1, which is simply equal to minus I, which is rotation by 180 degrees. And what is K inverse? So K inverse is 1 over the determinant of K, 1 over the determinant of the K times, I swap these two, doesn't make a difference, and I change the sign here. So this is plus 1 and this is minus 1. But what is the determinant of K? Determinant of K is 0, 0 plus 1. This is plus 1. So this is the determinant of K, which is 0, 1 and minus 1 and 0. So this is 0, 1, minus 1 and 0. And this is simply rotation by minus 90 degrees, because this is still cosine of minus 90. This is minus sine of minus 90, which is plus sine of 90. This is plus sine of minus 90, which is minus 90. And this is cosine of minus 90, which is 0. Okay, so lambda 1 equals lambda 2 here equals minus 1, because these are the elements on the main diagonal. Here we know that lambda 1 equals plus iota and lambda 2 equals minus iota. And here again lambda 1 equals minus iota or plus iota, and lambda 2 equals minus iota. You can check that this is actually what you get. Why? Because K inverse minus lambda I determinant is simply minus lambda is lambda square, and minus plus lambda equals 0, which implies lambda square equals minus 1. Maybe I write it in another way so that you are familiar with. This is minus lambda whole square. So this is equal to iota square, or lambda 1 equals plus iota and lambda 2 equals minus iota. Also K4 is the rotation through 360 degrees, and this should be equal to I. And let's see, it should be equal to I, and if I do K square 2 times, so this is equal to, which implies K square into K square, which is equal to minus I into minus I, which is equal to plus I, and diagonal, the corresponding diagonal element is going to be plus, in terms of K, is going to be I raised to power 4 minus I raised to power 4, which is equal to I square into I square, which is equal to minus into minus plus 1. This is 0. And this is again minus I minus 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 minus. So again this is 4i's plus minus into minus into minus into minus. So 4 times minus is plus, minus 1 raised to power 4 times is plus, and again I have I4, so this is 0 and this is 1. So all matrices have some meaning. These are not just some numbers, zeros and ones. And So you need to actually ponder over these results and see what these elements actually give you. Okay, so now counter proof. If ax equals lambda x and by equals some mu y, and what about this proof? So if I am saying, so my claim is eigenvalue of AB is lambda times mu. So this is the eigenvalue of AB. So my proof here is, I say let AB times x equals A times mu x, which is equal to mu times AX, which is equal to mu times lambda x. So I say AB has eigenvalue mu lambda. So what is wrong here? So what is wrong here is, so this is an incorrect approach. So this is incorrect. So it's an incorrect approach. Why? Because we have assumed that matrices share the eigenvector. We have assumed that the matrices share the eigenvector x. This is not true. So in general, this is not true. So let me give you an example. So A equals 0, 1, 0, 0, and B equals 0, 0, 0, 1. So eigenvalues both cases. So lambda 1 equals, B equals 0, 0, 1, 0. I'm sorry. 0, 0, 1, 0. So here lambda 1 equals lambda 2 equals 0. And here lambda 1 equals lambda 2 equals 0. So both have eigenvalues 0. What about AB? So AB is, so if we know our matrix multiplication, I am multiplying this matrix A by this column. When I do that, I'm only taking the second column here, so which is 1 and 0, and here there is no contribution. And BA is, so B times A, there is no contribution here, 0, 0, and then I'm picking the first column, which is 0 and 1. So AB is not equal to BA. So if AB is not equal to BA, what is the eigenvalue here? So eigenvalue here is lambda 1 is equal to 1 and lambda 2 is equal to 0. Here lambda 1 is equal to 1 and lambda 2 equals 0. Also, what is A plus B? A plus B equals A plus B equals 0, 1, 0, 1, 1, 0. And obviously A plus B equals B plus A. Here the eigenvalues are lambda square minus 1 equals 0. So this implies eigenvalues of A plus B are plus 1 here, so it's plus minus 1. So eigenvalues of A and B, here are zeros, but here the eigenvalues of A, B's are 1 and 0. They are not the same as zeros. Similarly, the eigenvalues here is A plus B is plus 1, and this is not equal to mu plus lambda. And when is this true actually? So however, if A, B and A plus B share same eigenvectors, share eigenvector, then eigenvalue, then eigenvalue, then eigenvalue is mu times lambda or mu plus lambda. This is only if they share the eigenvectors and if they share the same eigenvectors. If it's not, then obviously we can't have this. So we have another fact: diagonalizable matrices share same eigenvector, matrix S if and only if they commute. This implies AB equals BA. So if the matrices commute, and if you recall from our early discussion in this lecture, the normal matrices actually commute. So normal matrices commute, so and which includes the symmetric, the skew symmetric, the Hermitian symmetric, the Hermitian skew symmetric, the orthogonal and unitary. Since they commute, they share the same eigenvector. So what's the proof here? So if the matrices commute, then they share the same eigenvector matrix S. So proof is, since this is an if and only if, we have to prove both ways. So we say let A equals S lambda 1 S inverse. So they share the same matrix, and B equals S lambda 2 S inverse. This implies AB equals S lambda 1 S inverse S lambda 2 S inverse, which is equal to, so this is I. So this is S lambda 1 lambda 2 S inverse. And BA is obviously S lambda 2 lambda 1 S inverse. Since diagonal matrices commute, since lambda 1 lambda 2 equals lambda 2 lambda 1, this implies AB equals BA. So if they share the same eigenvector, S, then AB is equal to BA. Why? Because the diagonal matrix is complete. Okay. The other way is, the other side is, let AB equals BA. So let AB is equal to BA. Then we need to show that they share the same eigenvector matrix S, and AX equals lambda X. Then ABX equals BAX. Why? Because they commute, they are equal. So, or this is equal to B times lambda X, because A times X is lambda X, or this is equal to lambda times BX. X and BX are multiples of E. So this implies BX is a multiple of X. This implies X and BX are both eigenvectors. So this is BX and this is BX. So X and BX are both eigenvectors of A that share same eigenvalue lambda. If this is the case, so if eigenvalues are distinct, then eigenspaces are all one-dimensional, which simply means Bx is a multiple of X, Bx is a multiple of X, which means this is simply mu times X. So which implies which implies, so Bx is some mu x, which means B and mu eigenvalues. So these are the eigenvectors. So same eigenvector is shared by both and B, both A and B. So this implies x is an eigenvector, of A and B. So let's stop here, and next time, inshallah, we'll try to solve the difference equation, and maybe in the next, in the same or in the next lecture, we'll solve the differential equation. Um, uh, see how eigenvalues help us in solving the difference and the differential equations. Then we'll focus on complex matrices, what is so special about complex matrices, and then we'll move on to the similarity transformation and the triangular and the Jordan form. If you have any questions, again, you can send me an email, or we can discuss more on Mondays and Wednesdays. Thank you.